Good morning, everyone. It's a great pleasure to introduce the speakers for the second invited talk of this workshop. This will be Clotilde Biziere, and she will be talking about my favorite infinite state system, which are branching vector addition systems. I hope you will be convinced as well that this is the very best one.
Thank you. So we present an algorithm solving the reachability problem for two-dimensional branching VASS, and actually more precisely we will compute a semilinear representation of the reachability set of the two-dimensional branching VASS. So I think I don't need to recall everything about VASS, but the important point is that in this talk, all the run will be considered to start with counters at 0, and we also have one initial state which is fixed in the definition of a VASS. So we can talk about the reachability set of a VASS without any more parameters. And the main point of the talk is not VASS, but their extension with branching. So branching VASS is a VASS with, in addition, a second type of transition. They are binary transition, and they have two input states. So when you have P, Q, and R, they can be equal P and Q or P and R. And this transition means that whenever you can reach some counter value U in state P and V in state Q, then you can reach state R with a counter value U plus V. I have a kind of non-standard way of representing graphically branching VASS. So here in red, these two double arrow stands for one binary transition from P and Q to R. So you can see between state P and state R, we have a plus Q transition, meaning that when you are in state Q, you can go in state R and add any counter value reachable in state Q. So this transition is in some sense redundant compared to this one, but it will be useful to have both. And here you have the second binary transition from S and Q to Q. With this binary transition, the runs are no longer sequences of configuration, but now they are trees. So they start from the initial configuration on every leaf. When you have a unary node, it should be obtained from its check by applying a unary transition. And when you have a binary node, there should be a binary transition with the corresponding states, and this vector should be the sum of the vector of the children. And here this tree testifies that P53 is a reachable configuration in this VASS, which is branching VASS. So very little is known about reachability in branching VASS compared to ordinary VASS. The problem is known to be decidable in dimension 1, and the complexity is known, but from dimension 2, the decidability status is open. And another reason for studying reachability in dimension 2 is that dimension 2 is a very interesting particular case for ordinary VASS. The reachability set of a two-dimensional VASS is semilinear, and also a semilinear representation of it can be computed by the algorithm of Hopcroft and Pencio. So before we move to the main talk, is everyone at ease with semilinear states, or do I need to recall?
Semilinear sets are okay, but I didn't understand the definition of branching.
Ah, okay. So we move back. Maybe what part is?
Sorry. Bounded branch. I also didn't understand further that arrow. Can you make it space once more?
Okay, everything. Okay. So you have a VASS. You forget everything which is in red and green in this drawing, and then we will add new transition. This new transition have two input states and one output state, and they don't have any displacement. And then you have this rule that whenever you can reach this value U in state P and V in state Q, you can add them and go to state R. And that's why the runs are trees. So when you have a binary node in the reachability tree, it means that you have applied a binary transition.
Okay.
represents the additive closure of P, so you can take any vector in P and add it as many times as you want. And that's all. So actually we will not see only one algorithm, but two algorithms. The reason is that we had a very simple algorithm, but we couldn't prove termination for it. So we moved to a more complex algorithm, but it turned out that this more complex algorithm could be used to prove the termination of the first one, and the two algorithms are very closely related, so I think it is worth seeing both. So the plan of the talk will be a first part where we only describe the algorithms, and then in the second part we will do the proof of termination. So we'll start by an algorithm which I call the iterative algorithm, and then we will see another algorithm which is a generalization of the Hopcroft-Pensue algorithm. And before seeing this, I will just recall in the usual Hopcroft-Pensue algorithm. Okay, so the iterative algorithm starts from an observation. Here you have a branching VASS, and on the right you have the ordinary VASS that you obtain by removing the binary transition, as there is only one binary transition. And now imagine that you will find some reachable configuration in the VASS. So here it's Q13. I think you can reach it by taking this transition and this one. And now imagine that you add a new transition at the location where you have a plus Q transition with the displacement 1, 3. Then what happens to the reachability set of the branching VASS and of the VASS? Here, for the branching VASS, nothing changes, because if you have a reachability tree that uses this green transition, then you could replace it by a binary transition with a reachability tree for the configuration Q13, and so the reachability set doesn't change here. On the other hand, the reachability set can grow bigger on this side, but it remains included in the reachability set of the branching VASS because of what we've just said here. So the idea is that if we could just keep finding reachable configuration in the VASS and adding them again and again, we would obtain a VASS here which has the same reachability set as the branching VASS. But the problem is that there might be infinitely many reachable configurations, and you cannot add infinitely many transitions. So instead of adding them one by one, we will add them. We will add a whole linear set of reachable configuration at once. So we do the same. You find some reachable sets, some linear set of reachable configuration in the VASS. So here it's state Q, and the set of contours is 1, 3, and you have two periods, 3, 3, and 0, 1. And now you must find a way to add only finitely many states and transitions, and somehow add one transition for every configuration in this set. So the idea is to add one intermediary state, state S, and you add a loop for every period, and you have one transition. So here we want to add the transition at the location of the plus Q transition. So the input state is P, the output state is also P. So that's why we have these two green arrows. And you put the basis of the linear set 1, 3 in one of the two arrows. It doesn't matter which one. And here, once again, the reachability set of the branching VASS doesn't change, but the reachability set of the VASS can grow bigger while remaining into the reachability set of the branching VASS. So the algorithm will simply be, you start from the VASS obtained by removing the binary transition of the branching VASS. You compute the whole reachability set with the Hopcroft-Pensue algorithm. Then you add, for every linear set and double a row like this, you add this new set of transition. And in the end, you get a new VASS. And you do this once again. You do this until at 2 consecutive iterations you have the same reachability set in the VASS, and if at 2 consecutive iterations you have the same reachability set, it means that this VASS has the same reachability set as the branching VASS, and so you can stop. So the correctness of this algorithm is not very difficult, but it's very hard to prove that it terminates. So we will see the termination later. Now we'll just give a kind of characterization. It uses the notion of index of a tree. So this notion is not very common, but it's rather a notion for context-free grammar, but it can be extended to trees. The idea is that the index of a tree is the depth of the biggest complete binary tree that you can include in the tree you have. So it's you can define it from the leaves and then recursively. The index of a leaf is always 0. When you have a unary node, you just copy the index of the child. And when you have a binary node, there are 2 cases. Either the 2 children have different index, and in that case you take the maximal index of the 2 children, because if you want to insert a binary tree into such a tree, the best way is to insert it in the child which has the best index. But if the 2 children have the same index, then you increase the index by 1, because you could insert a binary tree of depth 1 here and 1 here, and then construct a binary tree of depth 2 here. So the link between this notion of index of a tree and the iterative algorithm is that the first iteration of the algorithm will find every configuration reachable in the branching VASS with a tree of index 0, and then the second iteration will find every configuration reachable with tree of index at most 1, etc. So the iterative algorithm terminates on a branching VASS if and only if there is a bound I max on the index, such that every configuration reachable in the branching VASS is reachable with a tree of index at most I max. So what we want to prove this property, and we will prove it with a second algorithm, which is an extension of the Hopcroft-Pensio algorithm. So no, I don't start with the Hopcroft-Pensio algorithm for branching VASS. I will first recall it for usual VASS. So the idea of the Hopcroft-Pensio algorithm is that the reachable configuration of a VASS can be naturally seen as a tree. The root is the initial configuration, and the children of a node are the configuration reachable from this configuration by applying only one transition. But of course we cannot compute the whole tree, because in general it can be infinite. So the idea of the Hopcroft-Pensio algorithm is that you will not have one configuration in every node, but a whole set of configuration, a linear set. For instance, in this example, you can see that you have an infinite branch of state P, where each time you increase the counters by 3 because of this loop. So instead of having this infinite branch, we will add this. In this set, we will have a linear set of period 3, 3 and of basis 0, 0. So on this example, the Hopcroft-Pensio tree will look like this. So here you have the root of the tree. Every time when you have a leaf, the set of configuration. Oh, I must explain. Do you have a tripole? The first coordinate is the state of the linear set of configurations. The second coordinate is the basis of the linear set. And here you have a set, and it is a set of period of the linear set. And the set of configuration contained in the leaf must be included in the set of configuration of some ancestor. So for instance, here it is clear that this linear set is included into this one. So I will explain how you build this tree. First, you start from a node which contains only one configuration, the initial configuration. And the first thing you do is you treat this node. So the first step of the treatment is to try to create periods. And we will have 4 rules for adding periods, which are a bit complicated. So if in this example, we will only need to use the first one. And the first one, the most obvious, is that you add the effect of positive cycles. So what I call positive cycle is cycles of positive weights. And when I mean positive for a vector, I mean that both coordinates are non-negative and that at least one is strictly positive. And I will say negative for a vector which is not positive in this sense. So here you try to add periods, so you can have, you see, you have one simple cycle of weight 3, 3. So you can add a period 3, 3. And you also have one positive cycle here of effect 0, 1. But you don't add the weight of this cycle because it's not executable from 0, 0. The problem, if you added the period 0, 1, is that this linear set of configuration will not contain only reachable configuration, so it would be a mistake in the algorithm. So we just have it, that we have added all the periods we could. And the second part of the treatment is to create children. So we want to create nodes that will contain every configuration reachable from one of the configuration in this set by applying one transition. So here there are 2 nodes. This one is really easy. You just apply the transition 3, 3 and you get this linear set of configuration. And this one is more complicated. When you start from 0, 0, you cannot apply the transition -2, 0. So the configuration 0, 0 yields nothing with this transition. On the other hand, if you start from any other configuration in this set, you can apply this transition. So that's how you get this set. And the general rule for doing this computation is you try to add the displacement of the transition to the basis. If it is possible, if the vector has both coordinates non-negative, then you do this. And if it's not possible, you try to add periods as little as possible, so that both coordinates are positive when you add the displacement of the transition. So here we've treated this node, and now we have 2 untreated nodes, and we treat them. For this one, it's very quick because the stop condition applies. The set of configuration contained in this node is included into the set of configuration of this node. So we check that before doing the treatment, and if the stop condition applies, we do nothing to this node. Then we move to this one, and this time we can add the effect of this cycle because now it is you can execute it. Then you add children. So if here you have only one children because there's only one transition you can apply. And then you have 2 children, and the stop condition applies at both children. So that was the easy example, but in general, you might need other rule for adding periods. For instance, in this example, you can add the period 3, 3 at the beginning, but you can do nothing with this cycle with rule 1, and if you do nothing, you can just apply the transition again and again. Maybe you need to add the period along the edge, but you would get an infinite branch. So we need to have a rule that does something with the negative cycles. And so the rule 2 is like this. When you have some periods, and when you have a simple negative cycle which is executable, you try to combine them in order to obtain a vector which is either vertical or horizontal. So here we can do only vertical. And if you can get such a vector, you add it to the set of periods. So in this example, you would get the period 0, 9, and you get it only here because you need the negative cycle to be executable. So you cannot add it here, and you cannot add it here. That was the first 2 rules. The rule 3 and 4 are a bit more complicated. It's not about, yes?
Why do you need this negative red vector to be immediately executable? On the previous slide.
It's how it is in the algorithm, but I agree that you could do better. You could, in some situation, you could add the period even if it's not executable. So that's just what the algorithm is.
I'm not completely convinced.
Yes, but that's what our content board did, and if I created this algorithm, I would have done differently. Okay. So now we have rule 3 and 4. So you can see on this example that the 2 previous rules are still not enough, because the problem in this VASS is that you have no positive cycle, it's no positive simple cycle. So when you arrive in state Q, you have nothing in your set of periods, and rule 2 was doing something with the negative cycle, but only if you already have a period. So here you could just take this edge twice and this edge once, and do this again and again. You would have an infinite branch with no period. So we need to add different rules. And so this rule is a bit special. If the current node has this label, so state Q, a basis B, and a set of period, and if you have an ancestor in the tree which has the same state and basis B prime, and if the difference between the bases is positive, then you can add this difference to the set of period, but only in certain situations. So the first one is when you have no period, and the second one is when this difference is an axis. So an axis is a word for the vertical or horizontal vector. And we want it to be a new axis, so vertical if you have no vertical periods, and horizontal if you have no horizontal periods in your set of periods. So these two conditions are a bit strange, but they only become clear when you see the termination proof. And maybe what I need to explain is why this operation is correct, why we will not add the periods the period needs to be something that we can iterate. So the reason is that the difference between these two configurations will be a union of cycles in the VASS that you can execute in such an order that in such an order so that the counters never become negative. So it's something you need to show by induction. So that was the approach-Mansu algorithm, and now we'll explain how we generalize it to branching VASS. So once again here I draw a branching VASS, and here on the right I draw the underlying VASS, and we will construct a tree. So once again we do a bit as in the first algorithm. We will add new transition to the VASS as we compute the Hopcroft-Mansu tree of this branching VASS. So here I change a bit the notation. I will give an identifier to every node of the Hopcroft-Mansu tree, and they will just be non-negative integers. And on the transition, I also indicate what is the node which gave this transition. So here, I have only one node in the tree, which is in state P. So for every plus P transition, I add a transition corresponding to this node, and it is labeled by the linear set contained in the node. So here the linear set is very simple, it's just the vector 0, so this transition is not so interesting. And then I do as before, I do the treatment, so I add periods. It is as before, and as I change the set of periods, I also update this transition. I create children, like before, the node is treated. Then I move to node 1, and as I start the treatment of node 1, I add a new transition corresponding to node 1. Then I do the same for node 2. And now I add the children, so I am in state Q, and there are 3 transitions, one normal unary transition, and 2 transitions that come from some node in the tree here. So here it will be a bit complicated. For the transition here, 2, 1, there is no problem, we do as before, but when we apply the transition 0 or the transition 1, we do something a bit special. We apply the transition, we only add the basis, because you must imagine that this notation is a shorthand for the kind of construction where you have an intermediary state and a loop with the period. So we don't add the period, we only add the basis. And in the Hopcroft-Franciaux tree, we add a new kind of dotted edge from 0 to the child. From 0 because 0 is the node associated to the transition. So actually this graph will not be a tree anymore, it will be a directed acyclic graph. When you take only the edges with a full line, it will be a tree. And when you include the edges with dotted line, this will be a directed acyclic graph. So our data structure is somehow a mixture of a DAG and of a tree. And the reason for this is that in some situation it will be useful to see a kind of symmetry between these two edges. This set of nodes could be obtained by applying the transition 0 to the node 2, but it can also be seen as applying the transition 2 from the node 0. So for some part of the algorithm it's useful to see this, but for some other parts you really want to break the symmetry, especially when we will prove the termination. We will want to apply Koenig's lemma and say that infinite tree of finite branching have an infinite branch, and here we will be able to apply it in the tree when we remove the edges with dotted line. And so here once again we add the children to node 2 using the transition related to node 1. So we have this new node which has its two parents. And that's how the algorithm goes. I don't go to the end because it would be very long. So also the difficult point for this generalization of Hopcroft and Montoy that we need to modify the rule for adding period. So I think essentially we don't modify them. This is only some technical and small modification that could become clear only if we go to the very detail of the proof. So you don't need to try to understand them and to remember them, I just tell them so that you have an idea. So the first modification, it's not really a modification, but you had this rule where you add the difference between the current basis and the basis of an ancestor. And here we do it not in the tree, but in the whole DAG. So that's the part when you want to use the symmetry. So that's just this, we do this choice. And then the rule 2 about negative simple cycle doesn't change. And the rule 3 about the case where the set of period is empty doesn't change it at all. But these two rules will be slightly modified. For rule 1, which is about adding the weight of simple positive cycle, we add a restriction which is maybe not very clear, but now the cycles are composed of two transitions, the unary transition of the branching VASS and the transition that we created during the algorithm that are associated to some node. And you can add the weight of such a cycle only if every node whose transition is used is a predecessor, an ancestor of the current node in the DAG. So here, for instance, you could add the weight of this cycle with node 3 and node 4 only at node 8 and 9, but not elsewhere. So that's the restriction. But actually this restriction was a bit too harsh, so we need to change, to reduce a bit the restriction. So now, yes, you don't need the cycle to be executable at the current node, but if it was executable before, but you could not add the period because of this constraint, then you are allowed to add this at the current node. So it's a bit complicated, but you don't need to remember this. And the second modification is that we extend a lot the rule 4. The rule 4 was about the difference between the current basis and the basis of an ancestor. And before it was just that you add it when the difference is an axis. Now we do, if this difference is negative, we do as we do in rule 2 with the negative simple cycles. And there is also when it is not an axis but almost an axis, something a bit like this where the basis B is smaller than some constant with one of its coordinates, then we can also add the difference. So you don't need to remember this, I just tell you what it is. So now we've seen the free algorithm. and we will prove that they terminate. So we'll do a very short part where we explain why the termination of the extended Hopcroft-Pensio implies the termination of the first algorithm. That's just for the motivation and it will not take time. Then we will see the proof of termination for the classical Hopcroft-Pensio algorithm. So I'm a bit sorry for this part because it will be long, but I really cannot explain what we did for branching VASS without going through it. And I will try my best to explain it as clear as possible. And finally, we will see how we can prove the termination of the algorithm for branching VASS, which is the main result of this presentation. Is there any question now about the algorithm? Okay, perfect. So first I will explain why we can get the termination of the first algorithm, the iterative algorithm, from the termination of the extended Hopcroft-Pensio algorithm. We had at the end of the iterative algorithm, you had this characterization with index of trees. So what we want to prove is that if the extended Hopcroft-Pensio algorithm terminates, then every reachable configuration of the VASS, there will be some bound on the index needed for a branching VASS to reach its configurations. So the general idea is that you can see the extended Hopcroft-Pensio algorithm as a back and forth between the Hopcroft and Pensio DAG and the VASS that gets new transition. At the beginning, you have in the DAG you have only the initial configuration in one node. So of course the initial configuration is reachable by a tree of index 0, and you have a VASS, which is a branching VASS without its binary transition. So of course this VASS can reach exactly the transition that are reachable by the branching VASS by tree of index 0. And then the first move is to add to the VASS a transition related to a node which is reachable by index 0. So then the VASS can reach configuration of index at most 1. And then based on the VASS, you add a new node in the Hopcroft and Pensio DAG. So this new node will be reachable with index at most 1. And each time you do a back and forth, the index on both sides will increase by 1. So I will try to explain this. First, you add a transition to the VASS, so the VASS can compute configuration reachable with index at most 1. Then you do the treatment of the node, so now this node contains configuration reachable with index at most 1. Then you modify again the VASS because you modified the node in the DAG. Then you create children, and since the children, yes, we need to prove something here, but the children will be reachable with trees of index at most 2 because the VASS is currently can reach configuration of index at most 2. And then you move to the treatment of node 1. So now you add a transition of index at most 2, so the VASS can reach configuration of index at most 3, and so on. So the proof of termination for the iterative algorithm from Hopcroft and Pensio is really short. The difficult point is to prove the termination of the Hopcroft and Pensio algorithm for branching VASS. So now I will recall the termination proof of the Hopcroft and Pensio algorithm. Okay. Yes?
We move on. Is this characterization with the index valid for higher dimension, or it's already known to break down?
Yes, we can generalize it to higher dimension, and I was planning to talk about it, but only in the conclusion.
Okay.
Okay, so you will see.
So this characterization that with the index, well, of course, many other details are very dimension 2 is fundamental for many things.
Yes.
But the index does go through. Okay.
Yes.
Okay.
So now we do the termination proof of the Hopcroft-Pensio algorithm for classical VASS. So the Hopcroft-Pensio algorithm is constructing a tree, and it is only adding new nodes or adding periods to current nodes. So if it doesn't even if it does not terminate, you can speak about the tree that it constructs. Maybe it is infinite. And proving the termination of the upcost and pursue algorithm consists in proving that the tree constructed is finite. So we want to prove that some tree is finite, and it is finite branching. So we can use Clotilde's lemma, and we suppose for contradiction that the tree is infinite, and we get an infinite branch. And not to reach the contradiction, the goal is to show that the stop condition should have applied at some node in the branch. The first thing we do is that we try to simplify this branch as much as possible. So we prove small lemmas. First, you can just, since there are finitely many states, you can extract a sub-branch where every node has the same state. So we do this. And now we will try to have the same set of period at every node. And the reason we can have the same set of period at every node is that the set of period in a branch will become constant from a certain depth. And to show this, you need to remember that every node inherits the period of its parent. So the set of period in one branch is a growing sequence. And you can see by checking every rule that the number of period that can be added to a node is bounded by a constant which depends only on the VASS. The first rule adds the weight of simple positive cycles, so you have finitely many in the VASS. So this rule can create only finitely many periods. Then the rule 4 and 2 create only axes, but they are only two different directions, and you only create new axes. So these two rules will create only finitely many periods in every branch. And this rule 3, you apply it at most once when the set of periods is empty in the branch. So you have a bound, the number of positive simple positive cycle plus 3 will be a bound on the number of vector in every node. So what you do is simply you remove finitely many terms, the terms that at which the set of period is still not the final value, and you get a sub-branch with constant state and constant set of periods. And the last small thing that we need to prove is that this set of period will not be empty. So here it's a consequence of rule 2, no, rule 3, which says that if the set of period is empty, and if the difference between the current basis and the basis of an ancestor is positive, then you add this difference. The idea is that if no period were added on the branch, since every node has the same state in this sub-branch, it would mean that this sequence of B and I is a bad sequence for the well quasi-order n squared, and so this is impossible. And now our goal, which was to show that the stop condition applies somewhere, becomes a bit simple to state. It simply means that some I made a mistake. It should be I greater than j. You want to prove that some basis is included in a linear set which is before in the branch. So it should be something of this form, but j should be smaller than I. So to prove this, we will need a geometrical lemma. And this lemma uses a new notion, the notion of cone generated by a set of period. So the definition is very similar to the additive closure, except that this time the coefficients are rational numbers, so it means that you add vectors, but you can cut them maybe in 2 or 3, and you just need to reach at the end a point with integer coordinates and even positive coordinates. So in this example, the cones is simply the set of points with integer coordinates contained in this green area. So that's why we call this a cone. And the lemma is about an infinite set for which there is S, for which there is a set of period P, such that two hypotheses are verified. The first one is that the set S should be stable by adding a period, and also the set S should be contained in a cone generated by the sets of period P, but maybe not started at the origin is not important. So if you have these two hypotheses, you are stable under the set of periods and you are included into some cone, then your set S is semi-linear and it is even more precise. This set is a union of set of periods, of linear set of periods P, and you can have finitely many bases.
So I'm sorry, Clotilde. So if P doesn't contain 0, then should it really
yes.
be S equals S plus P, or maybe S included in S plus P
0
or
is
something?
included in the set. When I wrote Q plus, I meant Q plus with 0 inside. Okay, I'm sorry, it's just...
So you assume that 0 is always included in P?
Yes.
Aha. No, but I'm talking about the first equation. S equals S plus P.
Yes.
Right?
The first equation here.
So if 0 is not in P,
yes.
then we have
Yes, I made a mistake. You should add 0 here.
0 into...
Or maybe you can replace the condition by S is equal to S plus P star.
Yes. I thought first I put P star and then I thought, oh, no, it's useless to...
So it should be P star, I
Yes.
see. Aha.
Okay, thank you. So I will just take quickly the proof, but it's not important. You can use this lemma as a black box if you prefer.
But yeah. Okay. So could you explain a bit slower? So first condition means that this S is stable by adding P star, and the second is what?
You are included into a
in
cone.
some cone.
So it's a set like this green region.
And then there, Okay.
So if you want to prove this lemma, the idea is to remove every vector of P which is not an extreme vector, so all the vector in the middle. Here you remove this vector here, and you just draw the lattice which is generated by the two remaining vectors, and this cuts the cone into cells that are identical, and that can be viewed as ordered as the order n squared with the product order. And each of these cells contains finitely many points with integer coordinates, so you can just choose one of them. And then you want to write the set of points in red as some b plus p star. So what you do is that you only need to add the minimal, to add the points that are in the minimal cells containing a point in red for the product order, and then just a fact about the product order on n squared, that there is no infinite, you have only finitely many minimal elements, and that's how you can get your finite set B here. So we go back to the proof of the Opcode-Pensio, determination of the Opcode-Pensio algorithm. Now the goal will be to apply this lemma and show the termination. Okay. So the reason why we want to apply this lemma, we'll try to take as a set S all the configurations that are contained in a node of the sub-branch. And if we can apply the lemma, this will imply that all the nodes contained in the branch are in fact contained into just finitely many nodes in the branch. And so once you've seen all these nodes, then at the next node, the stop condition will apply. So to apply the lemma, there are two hypotheses. One is easy to check. The first one, like obviously this state is stable by addition of P star. But the second one is more difficult to prove because we don't know how the bases are related. So we need to prove this hypothesis, and we do it in two steps. the first step is to prove this claim that every vertical or horizontal line contains finitely many bases of the branch of the infinite branch we took. So really, it's not the basis in the sub-branch, but the basis in the whole branch. There is a small difference. And if you manage to prove this, this would have two consequences. First, you can choose some large constant C, and then all the bases from some point will have both coordinates greater than this constant. And if you have large coordinates, this would mean that the branch will be much simpler, because to go from one node to the child, you don't need to add periods, and every cycle is always executable from the basis, so the branch will be much simpler to study. And the second consequence is that we make one step towards our goal to have every basis contained in one cone, because we will be able to choose that every basis in our sub-branch has both coordinates greater than the first basis of the sub-branch, and then it will be easier to compare this basis. We will show that all the bases will be contained in a cone which has the basis B and 0 as the basis, and which is generated by the set of period P.
Sorry, so do I understand correctly that if you prove a claim,
yes,
you will go to the point in which you already have seen all these, say, finitely many BIs
yes,
on these lines?
yes,
So you have nothing on this, like vertical and horizontal
yes,
lines, which are
exactly.
small. I see. So that, and then you want to apply lemma for this stuff only far away from the axis.
Yes, exactly. So I think I will just keep the proof. It's not very complicated. So now we imagine that we have proved this claim, and we want to prove our goal, which is that every basis is contained into the cone of periods P and of bases the first B and 0. So this is the same as proving that this difference is included into the cone generated by P. And what is important is that this difference can be seen as the effect of one cycle, not simple, but one cycle of the VASS. Because each time you go from one node to the child, you apply some transition. And here the two bases are related to the same state. So then we decompose this cycle into simple cycles, and we decompose the weight as a sum of weight of simple cycles, because the rules for adding periods are about simple cycles, so we do not know anything about cycles in general, but we only know something about simple cycles. So here I separate the cycles which are positive and the ones which are negative. And we will do something different for each of these two cycles. Wait. So for positive cycle, it's very easy. Just the rule 1 tells us that their weight is included in P. And since the set P is stable under addition, the whole sum of weight of simple positive cycle is included into the cone. So what will be a bit more difficult is to handle the weight of negative simple cycles. So what we are going to prove is this lemma, which says that if you start from a point in the cone, A here in blue, and you add the weight of one negative simple cycle, and if the result happens to be to have both coordinate positive, so it's okay in this situation, then the final point after applying the vector should remain in the cone. So this situation should not happen because we go out of the cone applying the weight of a simple negative cycle. And to prove that this situation never happened, you need to relate this to the rule 2. And so the relation is a kind of a geometrical proof. You have some period A, and you have some negative cycle W, and the question is, when will rule 2 apply to create a vertical axis or a horizontal axis? So to see this, you draw the line which goes through the origin and directed by the vector A, and you look whether W is above or below. If it is above, you can always construct a vertical axis, but you cannot construct a horizontal axis, because if you start from above the line and you apply the vector W, you will always remain above the line. And so the contrary, if you start from below the line, you can construct a horizontal axis, but you can never go above the line if you start below the line. And there is just a limit case when you are exactly on the line directed by A, then you can do nothing. You cannot create any vertical axis. Oh, there is a problem. Back. So here, if it were the case that the weight of the negative cycle could make you exit the cone, then it means that you start from above the line and you arrive below the line. So in fact, this vector can be combined with this one, the one of lowest slope, to create a horizontal axis. And so the cone should be enlarged, and it should be like as large as possible. And so there's no way of exiting the cone from below, and you have the same proof about exiting the cone above. Okay, so that was the proof for the termination of Markov-Pensu algorithm. You don't need to recall everything. And now I will explain how we extend this proof to branching VASS. But maybe I think we should do this after the break.
There will be a second part, but maybe you can also start questions right now.
I have a question. So it seems that the dimension 2 is really important because we are going to produce some axes. In dimension 3, what is the problem? I mean, is it? No.
I know there is a problem, but like explaining it right now is.
No, okay.
But I understand the problem with that approach is that just reachability set is not semi-linear, so you can't apply this, right?
Yes.
Yes.
You can apply.
But
But I mean, theoretically, let's assume that it were semi-linear. Would the algorithm still work? Well, the idea with generating axes would still have some problem in 3 dimensions, even if you give the hypothesis that it's semi-linear.
Even if it is semi-linear.
aha, right. So it's
So I think this was what Jerome's question was aiming to, but I don't know.
Maybe it's because the cone has in dimension 3 can be you can have several facets. I mean, it's
Yes.
difficult to characterize the cone. In dimension 2, you can provide just the extremal
Yes.
directions. So maybe this is one of the reasons.
Yes.
So towards going to higher dimension. So in this algorithm, you build better and better under approximations in the reachability set by saturations, adding at once a lot of reachable states. And here you use a lot the structure of inner sets. But suppose you have some algebra record that tells you how to add sub-VASSes.
Yes.
Then at some point you would have to check whether you reached the saturation, which would be an equivalence check of the reachability sets. This is undecidable in general.
Yes.
However, you know that one set is included in the other.
Yes.
So is this decidable? So equivalence of reachability sets, but if you are told by construction, for example, that one is included in the other.
No,
It's already undecidable. And sometimes problems become easier when you have such a problems. For context free grammars.
But here it is the same. I mean, it's not an inclusion of two similar sets, reachability set. It's somehow for the same vector addition system.
Okay.
Yeah.
I mean, it's a branching bus, but
The subsystem.
yes.
And well, I mean, here you have semi-linear representation for both things, right? So you don't invoke
Yeah, no,
any
that's
Euclid
yes,
elements.
yes,
Yes,
yes.
but in general, for higher dimension, I don't know if it's decided.
To przecinasz ten z tym i masz jeden zawarty w drugim.
I guess maybe we can have a break. I think we get started again at 11, right? 11.